Greetings students, and welcome back to my second lesson on Variational Calculus. In this video I'm going to derive the Euler-Lagrange equation, which allows you to find the stationary functions of a functional. So let's begin by supposing that we have 2 points A and B given by x1, y1 and x2, y2 respectively. What we want to do is find some function of x that makes the following functional or function of functions stationary. Now, in addition to making this functional stationary, there's another condition that we have to take into account when determining y. Can you see what that is? It's the boundary conditions. At x1, our function of x has to equal y1, and at x2, our function of x has to equal y2. So now that we've set up the situation, let's go ahead and begin our derivation/proof of the Euler-Lagrange equations. We will suppose that our desired function that makes I stationary and which satisfies the relevant boundary conditions is given by y. Another name for y is the extremal, because it's the particular function that makes our functional stationary or extreme. Now, what we're going to do here is introduce a function eta of x. The only condition on eta is that it has to be 0 at the boundaries x1 and x2. Otherwise, eta is just a completely random function. By the way, in this entire discussion, it's implied that these functions y, eta, and basically all the functions we're concerned with all have continuous second derivatives. So just keep that in mind. Anyway, what we're going to do is define a new function y bar given by our extremal y plus some parameter epsilon times the arbitrary function eta. Essentially, y bar represents a variation in the extremal y. And because eta is an arbitrary function, you can conclude that by extension y bar can also represent any arbitrary function. The only restriction on y bar arises from the restrictions we put on y and eta earlier on, and you can easily verify that y bar satisfies the exact same boundary conditions as y. Now, because of the parameter epsilon and the arbitrary function eta, this y bar can be interpreted as a mathematical entity representing a whole family of curves. Now what I want to do is find the particular curve in this family that makes our functional I stationary. Now one thing I want you to notice before I continue is that this quantity I depends only on the parameter epsilon. Why is that? Well, because the x gets integrated out from this definite integral, which means that once you integrate and apply your limits to end up with your I, the only parameter or variable remaining in the final expression is epsilon, because everything else depends on x. Now, my primary objective here is to make I stationary, but since I only depends on epsilon, making I stationary is equivalent to setting di d epsilon equal to 0. It's like single variable calculus. If you want a function to be stationary, just set its derivative to 0. But we already know what value of epsilon corresponds to a stationary I, and that's epsilon equals 0. Because remember, the function y of x was already assumed to be stationary beforehand, and so it's easy to see that when epsilon equals 0, the particular curve that we end up for y bar is our desired extremal y. Alright, so what we're going to do is use this fact that di d epsilon equals 0 at epsilon equals 0. We're going to use this fact to differentiate the integral expression for I, do some algebra, and eventually arrive at the Euler-Lagrange equation. Hopefully everything should be clear so far. Now, when the derivative of I with respect to epsilon is 0, then the derivative of this whole integral with respect to epsilon is 0. Obviously because I equals this integral by definition. Now, let's move this derivative inside, in which case we end up with a partial derivative with respect to epsilon. Now, y bar and y bar prime are the only variables or functions inside capital F which depend on epsilon. X is just an independent variable by itself, so what we can do is apply the chain rule of partial differentiation to end up with the integral from x1 to x2 of partial f partial y bar times partial y bar partial epsilon plus partial f partial y bar prime times partial y bar prime partial epsilon. And this integral at epsilon equals 0 has to be equal to 0. Let's copy-paste the expression for y bar that we defined above, which is just y bar equals y plus epsilon times eta. Now we also need to find the derivative of y bar prime. And the derivative of y bar is then just given by y prime x plus epsilon times eta prime x. If I take the partial derivatives of these expressions with respect to epsilon now, then I'll end up with eta and eta prime respectively. And let's plug them back into our expression for di d epsilon, and this is what we'll end up with. Alright, so now we need to simplify further. We'll take the second term in this integral and integrate it by parts separately. We'll have the first function, which is the partial of capital F with respect to y bar prime, times the integral of eta prime with respect to x, minus the integral of eta prime, times the derivative with respect to x of partial f partial y bar prime. And of course our limits of x1 and x2 would still be there. The integral of eta prime is just eta, so let's just plug that in. Now, we know from the boundary conditions on eta that at both x1 and x2, eta is just 0, so we can cancel out this first term in the integration by parts expression. And let's plug this remaining term back into the equation for di d epsilon, and here is what we'll end up with. We can take the eta common and end up with a factored expression for the integral. Now, when epsilon is 0, y bar is just equal to y by the definition of y bar, and we'll end up with this simplified expression for di d epsilon. And because eta is an arbitrary function, the only way this integral is guaranteed to be 0 is if partial f partial y minus the derivative with respect to x of partial f partial y prime is 0. And this equation is called the Euler-Lagrange equation. What it means is that if y of x is an extremal of the functional given by I up here, then y of x must satisfy this differential equation, this Euler-Lagrange equation. Just a couple of things to note. The Euler-Lagrange equation is a necessary condition for the function y of x to give a stationary functional. It is not a sufficient condition. Also, Euler-Lagrange only tells you the functions which make a functional stationary. It doesn't tell you about whether the functional becomes a maximum or a minimum. It doesn't tell you about the nature of the functions you determine by solving the Euler-Lagrange equation. The nature is something you'll have to infer or find out on your own using some other method. Anyway, that's it. We've successfully derived the Euler-Lagrange equation. If you have any questions or requests, please let me know in the comments below. And if you enjoyed the video, feel free to like and subscribe. This is the Faculty of Khan, signing out.